Tonight, we travel far across time and space. You don't need to follow every word. Just let the story move through you, like starlight through the endless void. This evening, we'll explore the quiet dance of black holes as they merge into one, a cosmic waltz that unfolds over millions of years, yet culminates in a moment so profound it sends ripples through the very fabric of space-time. Let your mind drift with these words, whether you're seeking sleep or simply a moment of calm. Contemplation beneath the stars. Imagine yourself lying on soft grass on a warm summer night, gazing upward at a sky filled with countless stars. The air is still, and the world around you has grown quiet. In this moment of peace, consider that somewhere, far beyond our vision, two massive objects are slowly drawing together in the darkness. Two black holes, separated by vast distances, yet bound by the gentle pull of gravity. Their story begins long before they meet, in the quiet lives of stars that once burned brightly. If we could somehow transport ourselves to a distant galaxy, billions of years in the past, we might witness an evening beneath two suns, a binary star system where massive blue giants circle one another in a celestial dance that has continued for millions of years. The light from these stars would bathe any nearby worlds in a soft, ever-changing glow, sometimes brighter when both stars appear in the sky together, sometimes dimmer as one sets while the other rises. The rhythm of day and night on such a world would follow complex patterns, a gentle alternation of light and shadow that might seem strange to our Earth-accustomed eyes. The stars themselves know nothing of their fate. They simply exist, converting hydrogen to helium in their cores, releasing energy in a process that has continued since their birth from vast clouds of cosmic gas. Their surfaces ripple with convection currents, like water simmering in a pot, but on scales so vast that entire worlds could fit within a single ripple. Occasionally, a prominence of hot plasma might arc outward from one star, a bridge of light reaching toward its companion before falling back again. These stars are massive, perhaps 40 or 50 times the mass of our Sun, and their lives will be correspondingly brief. Where our Sun might shine for billions of years, these giants will exhaust their fuel in mere millions. And what would it feel like to drift through the space between these stars? The void between them is not truly empty. Tenuous wisps of gas and dust float in the darkness, so sparse that we might call it a vacuum, yet still containing atoms and particles that have journeyed across light years. If you could somehow exist in this space without protection, you would feel neither hot nor cold, for heat, as we understand it, requires matter to transfer energy. And in the near vacuum of space, there is too little matter for meaningful transfer. Instead, you would experience the strange contradiction of being simultaneously exposed to the intense radiation of nearby stars, yet surrounded by the profound cold of the cosmos. In this gentle darkness, individual particles make their slow journeys. A simple hydrogen atom might drift for centuries, pushed by the faint pressure of starlight, until it encounters the gravitational influence of one of our massive stars. Its path bends ever so slightly as it falls into an orbit around the giant. Perhaps it will eventually be drawn into the star itself, adding its infinitesimal mass to the stellar furnace. Or perhaps it will continue its quiet orbit for millions of years more, a tiny satellite of a cosmic giant dot. As time passes, hundreds of millions of years, our massive stars begin to change. Their cores, having fused hydrogen into helium, now begin to fuse helium into carbon and oxygen. Their outer layers expand, cooling as they stretch outward, transforming the once blue giants into red supergiants. If we could observe them now, we would see two enormous red stars. Their surfaces cooler, but their total size vastly increased, now close enough that their outer atmospheres might almost touch. Their gravitational dance has brought them nearer to each other over the eons, their orbits decaying through the gentle friction of tidal forces and the subtle pressure of stellar winds. The light from these aging stars would appear different now, deeper in color, more reddish-orange than the brilliant blue of their youth. If planets orbit these giants, they would have been pushed outward as the stars expanded, their once temperate surfaces now cooler in the diminished light. Perhaps life might have evolved on such worlds during the stars' stable phases, only to face extinction as their suns transformed, or perhaps life adapted, finding new ways to survive in the changing conditions, moving deeper underground, or developing different biochemistries suited to the cooler temperatures and altered radiation. The binary stars continue their slow waltz, their enormous atmospheres now occasionally brushing against each other like the gentlest of caresses. This interaction transfers mass and angular momentum between the stars, further altering their evolution. The larger star might begin to pull material from its companion, creating a stream of gas that flows from one to the other. This transfer accelerates the evolution of both stars, hastening them toward their eventual fates in the depths of these stellar giants. Nuclear fusion continues its alchemical work. The helium in their cores, formed from the fusion of hydrogen over millions of years, now fuses into carbon. The carbon, in turn, fuses into neon, then oxygen, then silicon. Each stage burns hotter and faster than the last, as the star desperately tries to generate enough outward pressure to balance the relentless inward pull of gravity. But this process cannot continue indefinitely. Eventually, the core will begin to produce iron, and at this point, the star's fate is sealed. Iron is unique among the elements in the stellar furnace. When lighter elements fuse, they release energy. The process is exothermic, providing the outward pressure that supports the star against collapse. But iron fusion absorbs energy rather than releasing it. Once a star begins to accumulate iron in its core, its days are numbered. Without the energy from fusion to maintain outward pressure, gravity will soon win the battle that has raged since the star's birth. And then, in what seems like a moment in cosmic time, one of the stars reaches the end of its life. Having exhausted the fuel in its core, it can no longer support itself against the inward pull of its own gravity. The collapse begins slowly at first, the outer layers falling inward as the nuclear fires at the center sputter and fade. But as the core compresses, the collapse accelerates. In mere seconds, the heart of the star implodes, while the outer layers are blown outward in a supernova explosion that briefly outshines the entire galaxy. The light from this explosion would take time to reach any observers. If we were watching from a planet orbiting a nearby star, we might first notice a new point of light in the sky. brightening over hours or days until it outshines all other stars combined. The light would be intense enough to cast shadows even at night, turning darkness into an eerie twilight. Over the following weeks, the light would gradually fade, but the star that produced it would be forever changed. The supernova explosion seeds the surrounding space with heavy elements: carbon, oxygen, silicon, iron, and even heavier elements like gold and uranium, created in the extreme conditions of the explosion itself. These elements, scattered through space by the force of the blast, will eventually become part of new stars, new planets, and perhaps even new living beings. In this way, the death of stars enriches the cosmos, providing the raw materials for future generations of cosmic structures. What remains at the center depends on the star's mass. For our massive star, the remnant is a black hole, a region of space where gravity is so intense that nothing, not even light, can escape. The event horizon forms a boundary in space-time, marking the point of no return. Inside this boundary, space itself flows inward faster than the speed of light, carrying everything toward a central singularity where our current understanding of physics breaks down. The newly formed black hole is perhaps 15 times the mass of our Sun, yet compressed into a region smaller than a city. This transformation from star to black hole happens with remarkable speed. One moment, the core of the star is a ball of iron and nickel, perhaps the size of Earth, but containing several solar masses of material. The next moment, as nuclear reactions cease and gravity takes over, this core collapses. Electrons are forced into protons, forming neutrons and releasing neutrinos in a process called electron capture. The neutrons themselves are packed together so tightly that even neutron degeneracy pressure, the quantum mechanical force that normally prevents neutrons from occupying the same space, is overcome by gravity's pull. As the core continues to collapse, it crosses a critical threshold, the Schwarzschild radius, at which point the escape velocity exceeds the speed of light. Once this happens, an event horizon forms, and a black hole is born. The matter that formed the core continues to collapse, perhaps to a point of infinite density called a singularity. Though our current physics cannot describe what truly happens at the center of a black hole, the event horizon, meanwhile, marks the boundary beyond which no information can escape to the outside universe. The companion star, still in its red supergiant phase, continues its orbit around the now invisible partner. From a distance, it might appear as a single star, moving in a strange elliptical path around an empty point in space. But it is not alone. It is bound to its dark companion by the same gravitational threads that have connected them for hundreds of millions of years. This surviving star now experiences new influences from its black hole companion. The intense gravitational field might begin to pull material from the star's outer atmosphere, creating a stream of gas that flows toward the black hole. As this gas approaches the event horizon, it doesn't fall directly in, but instead forms an accretion disk, a flattened, spiraling structure of superheated plasma. The inner regions of this disk can reach temperatures of millions of degrees, emitting X-rays and other high-energy radiation as the material gradually spirals inward. If we could observe this system from a safe distance, we would see a strange sight, a red supergiant star orbiting an invisible point, with a glowing disk of hot gas surrounding that point. The disk would appear brightest at its inner edge, closest to the black hole, and would gradually fade toward its outer regions. Jets of material might shoot outward from the poles of the black hole, perpendicular to the accretion disk, carrying away some of the energy and angular momentum of the infalling matter. The fate of the companion star is now accelerated by its interaction with the black hole. The loss of mass to the accretion disk alters its evolution, potentially hastening its own end. And when that end comes, perhaps millions of years later, perhaps much sooner, it too will explode as a supernova, leaving behind a second black hole in time. Perhaps millions of years later, the second star also reaches the end of its life. Another supernova illuminates the galaxy, and a second black hole forms. Now we have two dark objects orbiting each other, invisible to direct observation, their presence detectable only by their gravitational effects on surrounding matter and light. These two black holes begin a new phase of their cosmic dance. Their orbits slowly decay as they radiate gravitational energy, drawing them closer together over millions of years. This is the slow dance of gravity, patient, inevitable, governed by the elegant mathematics that Albert Einstein described. In his theory of general relativity, the fabric of space-time itself curves around these massive objects, like heavy weights placed on a stretched rubber sheet. The deeper the curve, the stronger the gravitational pull. And our black holes create profound wells in this cosmic fabric. Einstein's equations tell us that space-time is not merely a static stage upon which cosmic events unfold, but a dynamic participant in those events. The curvature of space-time tells matter how to move, while matter tells space-time how to curve. This reciprocal relationship, expressed in the field equations of general relativity, describes a universe where space and time are woven together into a single continuum, flexible and responsive to the presence of mass and energy. The mathematics of general relativity is both beautiful and complex. At its heart is the idea that gravity is not a force in the conventional sense, but rather a manifestation of the curvature of space-time. Massive objects like stars and black holes create depressions in this fabric, and other objects move along the straightest possible paths through this curved geometry. These paths, called geodesics, appear to us as orbits or trajectories influenced by gravitational attraction. For our binary black holes, their mutual gravitational attraction is actually the result of each one following a geodesic through the space-time curved by the other. They orbit their common center of mass, each one moving along the path of least resistance through a space-time geometry that is constantly changing due to their motion. This dance is described by Einstein's field equations, a set of 10 coupled, nonlinear partial differential equations that relate the curvature of spacetime to the distribution of mass and energy. As our black holes orbit each other, they create ripples in this space-time fabric, gravitational waves that propagate outward at the speed of light. These waves are incredibly subtle, stretching and compressing space itself by fractions smaller than the width of an atomic nucleus. They carry energy away from the binary system, causing the black holes to spiral gradually closer together. The process is exquisitely slow for most of their lives. The black holes might orbit each other for billions of years, with barely perceptible change. The nature of these gravitational waves is worth contemplating. Unlike sound waves, which require a medium like air or water to propagate, gravitational waves travel through the vacuum of space. They are not waves in a medium, but waves of the medium oscillations in the fabric of space-time itself. As a gravitational wave passes through a region of space, it alternately stretches and compresses distances in directions perpendicular to its direction of travel. The amplitude of these waves, the amount by which they stretch and compress space, depends on the masses of the orbiting objects, their separation, and their orbital speed. For our binary black holes, widely separated and moving relatively slowly for most of their lives together, the waves are extremely weak. But as they spiral closer together and their orbital speed increases, the waves grow stronger and higher in frequency. Imagine standing at the edge of an event horizon, if such a thing were possible. The event horizon itself is not a physical surface, but a boundary in space-time. If you could somehow hover just outside this boundary, you would experience strange effects. Looking outward, away from the black hole, the universe would appear normal, though the light from distant stars would be blue-shifted by the black hole's gravity well. But looking inward, toward the black hole, you would see ... nothing. An absence more profound than darkness, for darkness implies the possibility of light. The event horizon marks the point where the future light cone, all possible paths that light could take moving forward in time, points entirely inward. No light from events inside the horizon can ever reach you. The concept of a light cone is central to understanding the causal structure of spacetime. At any point in spacetime, the light cone consists of all possible paths that light could take from that point, both into the future light cone, and from the past light cone. Because nothing can travel faster than light, the light cone defines the limits of causal influence. Events outside your past light cone cannot have influenced you, and events outside your future light cone cannot be influenced by you. Near a black hole, these light cones become distorted by the extreme curvature of spacetime. As you approach the event horizon, your future light cone tilts increasingly inward, until at the horizon itself, the edge of the cone aligns exactly with the horizon. Inside the horizon, all future directed paths, even those of light, lead inexorably toward the central singularity. This is why nothing, not even information, can escape from inside a black hole. Time itself behaves strangely near a black hole. From the perspective of a distant observer, a clock falling toward the event horizon would appear to tick more and more slowly, its light becoming increasingly redshifted until it seems to freeze at the horizon itself. But for someone falling with the clock, time would pass normally. They would cross the event horizon without noticing any particular boundary. Though once inside, all possible futures would lead inexorably toward the central singularity. This time dilation effect is not unique to black holes. It occurs in any gravitational field, including Earth's, though to a much lesser degree. GPS satellites, for instance, must account for the fact that time passes slightly faster in orbit than on Earth's surface. But near a black hole, the effect becomes extreme. If you were to hover near the event horizon of a stellar mass black hole, each second of your time might correspond to minutes, hours, or even years for observers far away from the black hole. Our orbiting black holes each have their own event horizon, their own region of no return. As they spiral closer together, these horizons remain separate, two distinct bubbles in spacetime. Each black hole may also be rotating, spinning on its axis, a property inherited from the angular momentum of the star that formed it. A rotating black hole drags the fabric of spacetime around with it, a phenomenon called frame dragging. Near the event horizon of such a black hole, space itself is in motion, flowing like a river around a whirlpool. The mathematics describing rotating black holes was worked out by Roy Kerr in 1963, resulting in what we now call the Kerr metric. A rotating black hole has not one but two important boundaries: the event horizon, as before, and a new region, called the ergosphere. The ergosphere extends outward from the event horizon, reaching farthest at the black hole's equator and meeting the horizon at the poles. Within the ergosphere, space-time is dragged around by the black hole's rotation with such force that nothing can remain stationary with respect to distant stars. Everything must rotate in the same direction as the black hole, though not necessarily at the same rate. This rotation happens in perfect silence. Indeed, black holes are the quietest objects in the universe, for no sound can escape them, and the vacuum of space carries no sound waves. Their movement through space, their spinning, their gradual approach toward each other, all of this happens in a silence more complete than any we can experience on Earth. Even as they create gravitational waves, these ripples in spacetime are not sound, but a much more fundamental disturbance, detectable only with the most sensitive instruments humans have ever built. And then, in what seems like a moment in cosmic time, one of the stars reaches the end of its life. Having exhausted the fuel in its core, it can no longer support itself against the inward pull of its own gravity. The collapse begins slowly at first, the outer layers falling inward as the nuclear fires at the center sputter and fade. But as the core compresses, the collapse accelerates. In mere seconds, the heart of the star implodes, while the outer layers are blown outward in a supernova explosion that briefly outshines the entire galaxy. This final moment in a star's life unfolds with both violence and beauty. For billions of years, the star has maintained a delicate balance, the outward pressure from nuclear fusion in its core precisely counteracting the inward pull of its own immense gravity. But now, that balance has been irreversibly disrupted. The iron core, unable to generate energy through fusion, can no longer support the weight of the star above it. The collapse that follows happens with astonishing speed. As the core compresses, the density increases exponentially. Electrons, once free to move between atoms, are forced into atomic nuclei, combining with protons to form neutrons and releasing ghostly particles called neutrinos in the process. These neutrinos, nearly massless and barely interacting with matter, carry away enormous amounts of energy. For a brief moment, the collapsing star becomes the most powerful neutrino source in the galaxy, though these particles pass through ordinary matter so easily that they would flow through a light year of lead with only a small chance of interaction. In falling outer layers of the star reach velocities approaching a quarter of the speed of light as they hurtle toward the core. When they strike the newly formed neutron core, now compressed to nuclear densities, they bounce back outward. This bounce, combined with the pressure from the flood of neutrinos pushing outward, drives the spectacular supernova explosion. The outer layers of the star are ejected into space at thousands of kilometers per second, carrying with them elements forged both during the star's life and in the extreme conditions of the explosion itself. From a safe distance, this explosion would unfold like a cosmic flower blooming in slow motion. The initial flash might last only seconds, but the expanding shell of stellar material would continue to glow for weeks or months as radioactive elements created in the explosion decay and release energy. This glowing remnant, called a supernova remnant, can remain visible for thousands of years as it expands and interacts with the surrounding interstellar medium. The light from the supernova carries information about the elements present in the explosion. By analyzing this light, breaking it into its component wavelengths, astronomers can identify specific elements and even isotopes created in the star's death. Carbon, oxygen, silicon, iron, these and many other elements are scattered into space, enriching the interstellar medium from which future stars and planets will form. In a very real sense, the deaths of stars provide the building blocks for new worlds and eventually for life itself. What remains at the center depends on the star's mass. For our massive star, the remnant is a black hole, a region of space where gravity is so intense that nothing, not even light, can escape. The event horizon forms a boundary in space-time, marking the point of no return. Inside this boundary, space itself flows inward faster than the speed of light, carrying everything toward a central singularity where our current understanding of physics breaks down. The newly formed black hole is perhaps 15 times the mass of our Sun, yet compressed into a region smaller than a city. The formation of this black hole represents one of the most extreme transformations in nature. The star's core, once a sphere of iron, perhaps the size of Earth, collapses beyond the density of atomic nuclei, beyond even the density of neutron stars. When the mass of the collapsing core exceeds about 3 solar masses, no known force can halt the collapse. The core continues to compress, and as it shrinks, its gravitational field at the surface grows stronger. Eventually, the escape velocity, the speed needed to break free from the gravitational pull, exceeds the speed of light. At this point, an event horizon forms, and a black hole is born. The event horizon is not a physical surface, but a boundary in spacetime. It marks the point where the curvature of spacetime becomes so extreme that all future paths lead inward. Imagine a river flowing toward a waterfall, moving faster and faster as it approaches the edge. At some point, the water flows too quickly for a swimmer to make progress against the current. The event horizon is like this point of no return once crossed. The direction outward no longer exists as a possibility. The size of the event horizon, called the Schwarzschild radius for a non-rotating black hole, is directly proportional to the black hole's mass. For our 15 solar mass black hole, the event horizon would be about 45 kilometers in radius, small enough to fit within the boundaries of a modest city, yet containing a mass 15 times greater than our Sun. This incredible density illustrates the extreme nature of black holes. They represent the ultimate concentration of matter and energy possible in our universe, beyond the event horizon. Toward the center of the black hole lies a region where our current understanding of physics breaks down, according to Einstein's theory of general relativity. The matter that formed the black hole continues to collapse, eventually reaching a point of infinite density called a singularity. At this singularity, space-time curvature becomes infinite, and the known laws of physics cease to provide meaningful descriptions. Many physicists believe that a complete theory of quantum gravity, which would unite quantum mechanics and general relativity, is needed to understand what truly happens at the center of a black hole. The newly formed black hole might not be visible to direct observation, but its presence would be revealed through its effects on surrounding matter and light. If gas or dust from the supernova remnant falls toward the black hole, it would form an accretion disk, a flattened, spiraling structure of superheated material. As this material orbits closer and closer to the event horizon, it accelerates to tremendous speeds and heats to millions of degrees, emitting X-rays and other high-energy radiation. These emissions can be detected by telescopes, providing evidence of the black hole's existence. The companion star, still in its red supergiant phase, continues its orbit around the now invisible partner. From a distance, it might appear as a single star moving in a strange elliptical path around an empty point in space. But it is not alone. It is bound to its dark companion by the same gravitational threads that have connected them for hundreds of millions of years. This surviving star now experiences a different relationship with its companion. Where once there were two visible stars exchanging radiation and perhaps even material, now there is a visible star orbiting an invisible point. The black hole's gravity remains, pulling on the surviving star just as the original star did, but its interaction with its environment has fundamentally changed. The red supergiant, with its extended atmosphere, might begin to lose material to the black hole. As the star orbits, the black hole's gravity pulls more strongly on the near side of the star than on the far side. This differential pull, called a tidal force, can draw material from the star's outer layers. This material doesn't fall directly into the black hole, but forms a stream that gradually spirals inward, forming an accretion disk around the black hole. The accretion process releases enormous amounts of energy, up to 40% of the rest mass energy of the infalling material, far more efficient than the nuclear fusion that powers stars. This energy heats the inner regions of the accretion disk to temperatures of millions of degrees, causing it to emit X-rays and other high-energy radiation. If we could observe this system, we would see a red supergiant star orbiting a point of intense X-ray emission, a telltale signature of a black hole feeding on stellar material. The fate of the binary system now depends on several factors: the separation between the star and black hole, the mass of the surviving star, and how much material is transferred between them. In some cases, the interaction might hasten the evolution of the surviving star, causing it to exhaust its fuel more quickly than it would have in isolation. In other cases, the black hole might strip away the star's outer layers, leaving behind a smaller, hotter stellar core. In time, perhaps millions of years later, the second star also reaches the end of its life. Another supernova illuminates the galaxy, and a second black hole forms. Now we have two dark objects orbiting each other, invisible to direct observation. Their presence detectable only by their gravitational effects on surrounding matter and light. The death of the second star mirrors that of the first in many ways. The exhaustion of nuclear fuel, the collapse of the core, the supernova explosion. But there are differences, too. The star's evolution has been influenced by its black hole companion, perhaps losing mass to it over millions of years. The supernova itself might be asymmetrical, as the black hole's gravity pulls more strongly on the near side of the exploding star, and the resulting black hole forms in the presence of another black hole, immediately creating a binary black hole system rather than needing to encounter its partner later. The newly formed binary black hole system is a remarkable object. Two regions of extremely curved spacetime orbiting a common center of mass. Each black hole has its own event horizon, a boundary beyond which nothing can escape. Between them stretches a region of highly distorted spacetime where the gravitational fields of the two black holes combine in complex ways. If matter is present in this region, perhaps remnants from the second supernova, it would follow intricate orbital paths, influenced by both black holes simultaneously. These two black holes begin a new phase of their cosmic dance. Their orbits slowly decay as they radiate gravitational energy, drawing them closer together over millions of years. This is the slow dance of gravity, patient, inevitable, governed by the elegant mathematics that Albert Einstein described in his theory of general relativity. The fabric of spacetime itself curves around these massive objects like heavy weights placed on a stretched rubber sheet. The deeper the curve, the stronger the gravitational pull. And our black holes create profound wells in this cosmic fabric. Orbital decay of binary black holes is a direct consequence of Einstein's theory. According to general relativity, accelerating masses produce ripples in spacetime called gravitational waves. These waves carry away energy and angular momentum from the binary system, causing the black holes to spiral gradually closer together. The process is analogous to the way orbital energy is lost in binary star systems through electromagnetic radiation, but with gravitational waves playing the role of light. For most of their orbital evolution, this decay is extremely slow. When the black holes are widely separated, perhaps by light years, the gravitational waves they emit are very weak, and the orbit changes imperceptibly over millions or even billions of years. But as the black holes draw closer together, the process accelerates. The gravitational waves become stronger, carrying away more energy, causing the black holes to spiral inward more rapidly. This creates a feedback loop that eventually leads to the merger of the two black holes. Einstein's equations tell us that spacetime is not merely a static stage upon which cosmic events unfold, but a dynamic participant in those events. The curvature of spacetime tells matter how to move, while matter tells spacetime how to curve. This reciprocal relationship, expressed in the field equations of general relativity, describes a universe where space and time are woven together into a single continuum, flexible and responsive to the presence of mass and energy. The field equations of general relativity are among the most beautiful and profound in all of physics. Written in the language of tensor calculus, they can be expressed in a deceptively simple form. G equals 8t, in units where the gravitational constant and speed of light are set to 1. The left side, G, represents the curvature of spacetime, while the right side, T, represents the distribution of matter and energy. This elegant equation encapsulates the fundamental insight of general relativity, that gravity is not a force in the conventional sense, but a manifestation of the geometry of spacetime. Solving these equations for complex systems like binary black holes is extraordinarily difficult. The equations are nonlinear, meaning that the curvature caused by two black holes is not simply the sum of the curvatures that each would produce individually. Instead, the curvatures interact in complex ways, requiring sophisticated mathematical techniques and powerful computers to model accurately. Only in recent decades have physicists developed the numerical methods needed to simulate the final orbits and merger of binary black holes. As our black holes orbit each other, they create ripples in this space-time fabric, gravitational waves, that propagate outward at the speed of light. These waves are incredibly subtle, stretching and compressing space itself by fractions smaller than the width of an atomic nucleus. They carry energy away from the binary system, causing the black holes to spiral gradually closer together. The process is exquisitely slow for most of their lives. The black holes might orbit each other for billions of years with barely perceptible change. Gravitational waves are fundamentally different from electromagnetic waves like light or radio. While electromagnetic waves travel through spacetime, gravitational waves are oscillations of spacetime itself. They alternately stretch and compress distances in directions perpendicular to their direction of travel. If a gravitational wave traveling along the z-axis passes through a ring of particles arranged in a circle in the xy plane, the ring would be stretched into an ellipse along the x-axis while being compressed along the y-axis, then stretched along the y-axis while being compressed along the x, and so on as the wave passes. The pattern of gravitational waves emitted by a binary black hole system carries detailed information about the system, the masses of the black holes, their spins, the shape of their orbit, and their distance from Earth. By analyzing these waves, scientists can reconstruct many properties of the source, even though the black holes themselves emit no light. This is gravitational wave astronomy, a new way of observing the universe that doesn't rely on electromagnetic radiation. For binary black holes, widely separated, the gravitational waves they emit have very low frequencies, perhaps one cycle every few hours or days, corresponding to the orbital period of the system. As the black holes spiral closer together, both the amplitude and frequency of the waves increase. In the final moments before merger, when the black holes are separated by just a few hundred kilometers, they might orbit each other hundreds of times per second, producing gravitational waves with frequencies in the audible range, though still far too subtle to detect without specialized instruments. Imagine standing at the edge of an event horizon, if such a thing were possible. The event horizon itself is not a physical surface, but a boundary in spacetime. If you could somehow hover just outside this boundary, you would experience strange effects. Looking outward, away from the black hole, the universe would appear normal, though the light from distant stars would be blue-shifted by the black hole's gravity well. But looking inward, toward the black hole, you would see ... nothing. An absence more profound than darkness, for darkness implies the possibility of light. The event horizon marks the point where the future light cone, all possible paths that light could take moving forward in time, points entirely inward. No light from events inside the horizon can ever reach you. The experience of hovering near an event horizon would be physically impossible for a human being. The tidal forces, the difference in gravitational pull between your feet and your head, would stretch your body into a long, thin strand, a process whimsically called spaghettification by physicists. Even if you could somehow resist these forces, the energy required to maintain your position against the black hole's gravity would be astronomical. And yet, thought experiments like this help us understand the extreme nature of black holes and the space-time around them. From your hypothetical vantage point near the event horizon, time itself would appear distorted. Your clock would tick normally, according to your own perception, but if you could somehow observe a clock far away from the black hole, it would appear to run faster than yours. Conversely, to a distant observer watching you, your clock would appear to run increasingly slowly as you approached the event horizon, eventually appearing to freeze completely if you reached the horizon itself. This time dilation effect is a direct consequence of the curvature of space-time near massive objects. The view looking inward toward the black hole would be unlike anything in ordinary experience. The event horizon is not a physical surface that reflects or emits light. It is a boundary in space-time beyond which no events can be observed from the outside looking toward this boundary. You would see what? Not darkness in the conventional sense, for darkness is the absence of light reaching your eyes and implies the possibility of light. The event horizon represents something more profound, a region from which no information of any kind can reach you. Our visual intuitions, evolved in the gentle gravitational field of Earth, fail us when confronted with such an extreme environment. Perhaps the closest analogy in everyday experience would be looking toward the edge of your visual field. You don't see darkness at the periphery of your vision. You simply don't see at all beyond a certain point. The event horizon might present a similar kind of absence, a region where the concept of seeing ceases to have meaning. Or perhaps it would appear as a perfect black sphere, absorbing all light that falls upon it, and reflecting none, set against the background of stars, distorted by gravitational lensing around the black hole. These thought experiments highlight the profound strangeness of black holes, objects so extreme that they challenge not just our intuitions, but the very foundations of our physical theories. At the event horizon and beyond, general relativity and quantum mechanics, our two most successful physical theories, come into conflict. Resolving this conflict is one of the great challenges of modern physics, potentially pointing the way toward a unified theory of quantum gravity that would describe nature at all scales and in all conditions, even the extreme environment of black holes. Time itself behaves strangely near a black hole. From the perspective of a distant observer, a clock falling toward the event horizon would appear to tick more and more slowly, its light becoming increasingly redshifted, until it seems to freeze at the horizon itself. But for someone falling with the clock, time would pass normally. They would cross the event horizon without noticing any particular boundary. Though once inside, all possible futures would lead inexorably toward the central singularity. This profound difference in temporal experience illustrates one of the most fascinating aspects of Einstein's relativity, that time is not absolute but relative, flowing at different rates depending on gravity and motion. Near a black hole, where space-time curvature reaches extreme values, these relativistic effects become dramatically apparent. If you were to watch a friend fall toward a black hole's event horizon, you would see their movements gradually slow, their voice deepen, and eventually fade. Your perspective, they would never quite reach the horizon, instead appearing to move ever more slowly as they approach it. Yet, from your friend's perspective, nothing unusual would happen to time. Their watch would tick at its normal rate, their thoughts would flow as always, and they would cross the event horizon without experiencing any local discontinuity in the laws of physics. This seeming paradox arises because the very concept of simultaneity, what events happen at the same time, breaks down in curved spacetime. Events that appear simultaneous to one observer may occur at different times for another, depending on their relative positions and states of motion. The mathematics describing this time dilation effect follows directly from Einstein's field equations. For a non-rotating black hole, described by the Schwarzschild metric, the time dilation factor at a distance r from the center is given by square root 1 to gm rc squared, where g is the gravitational constant, m is the black hole's mass, and c is the speed of light. As r approaches the Schwarzschild radius to gm per c squared, this factor approaches 0, meaning that time, as measured by a distant observer, appears too slow to a standstill. This time dilation has practical consequences for any matter. Falling into a black hole. From an external perspective, infalling material appears to slow down as it approaches the horizon, forming what's called a frozen star. The radiation from this material undergoes extreme redshifting, shifting from visible light to infrared, then to microwave, and eventually to radio frequencies too low to detect. The black hole appears to grow darker and darker, but never completely black. For the infalling observer, however, the journey continues normally. They would pass through the event horizon without feeling anything special at that boundary. No membrane to break through, no sudden change in forces. The horizon is not a physical surface, but a boundary in spacetime, invisible to those who cross it. Only after crossing would they realize their fate is sealed, as they notice that all paths forward in time, even those of light rays, curve inexorably toward the central singularity. The journey from the event horizon to the singularity would be brief from the infalling observer's perspective, perhaps just seconds for a stellar mass black hole. During this final plunge, they would experience ever-increasing tidal forces, differences in gravitational pull between their head and feet that would eventually stretch them into a long, thin strand of elementary particles. This process, sometimes called spaghettification, would occur before reaching the singularity itself, where our current theories predict that space-time curvature becomes infinite and the known laws of physics break down. Some theoretical physicists speculate that quantum effects might prevent the formation of a true singularity, perhaps replacing it with an extremely dense but finite quantum state. Others propose more exotic possibilities, that the interior of a black hole might connect to another region of spacetime through a wormhole, or that information falling into a black hole might be preserved in subtle quantum correlations in the Hawking radiation that black holes are theorized to emit. These questions lie at the frontier of theoretical physics, where general relativity and quantum mechanics meet, and their resolution may require a full theory of quantum gravity. Our orbiting black holes each have their own event horizon, their own region of no return. As they spiral closer together, these horizons remain separate, two distinct bubbles in spacetime. Each black hole may also be rotating, spinning on its axis, a property inherited from the angular momentum of the star that formed it. A rotating black hole drags the fabric of spacetime around with it, a phenomenon called frame dragging. Near the event horizon of such a black hole, space itself is in motion, flowing like a river around a whirlpool. The rotation of a black hole introduces new complexities to its spacetime geometry, while a non-rotating Schwarzschild black hole is perfectly spherical. With an event horizon at the Schwarzschild radius, a rotating Kerr black hole is oblate, slightly flattened at the poles and bulging at the equator. Its event horizon is smaller than that of a non-rotating black hole of the same mass, and it's surrounded by a region called the ergosphere, where space itself rotates. The ergosphere extends from the event horizon outward, reaching farthest at the black hole's equator and meeting the horizon at the poles. Within this region, spacetime is dragged around by the black hole's rotation with such force that nothing, not even light, can remain stationary with respect to distant stars. Everything must rotate in the same direction as the black hole, though not necessarily at the same rate. This doesn't mean objects are forced to fall into the black hole. They can still escape from the ergosphere, unlike the event horizon, but they cannot remain stationary. This frame-dragging effect creates possibilities that don't exist around non-rotating black holes. In 1969, Roger Penrose proposed a mechanism, now called the Penrose process, by which energy could be extracted from a rotating black hole. If an object in the ergosphere splits into two pieces, with one falling into the black hole and the other escaping to infinity, the escaping piece can emerge with more energy than the original object had. This extra energy comes from the black hole's rotational energy, causing it to spin more slowly. The mathematics describing rotating black holes was developed by Roy Kerr in 1963, resulting in the Kerr metric, a solution to Einstein's field equations that describes the spacetime geometry around a rotating black hole. For a maximally rotating black hole, the event horizon shrinks to half the size it would have for a non-rotating black hole of the same mass. Such extreme rotation might be common in nature. Simulations suggest that black holes formed from stellar collapse often spin at close to the maximum possible rate when two rotating black holes orbit each other. Their individual frame-dragging effects combine in complex ways. If their spins are aligned with each other and with their orbital angular momentum, the system evolves relatively smoothly. But if their spins are misaligned or anti-aligned, the resulting dynamics can be chaotic, with the spin axis and orbital plane precessing in complicated patterns. These effects become increasingly important as the black holes approach merger, influencing both the final stages of their inspiral and the properties of the merged black hole. This rotation happens in perfect silence. Indeed, black holes are the quietest objects in the universe, for no sound can escape them, and the vacuum of space carries no sound waves. Their movement through space, their spinning, their gradual approach toward each other, all of this happens in a silence more complete than any we can experience on Earth. Even as they create gravitational waves, these ripples in space-time are not sound, but a much more fundamental disturbance, detectable only with the most sensitive instruments humans have ever built. The silence of black holes is profound and multifaceted. Not only do they emit no sound, for sound requires a medium like air or water to propagate, and space is nearly a perfect vacuum, but they also trap all forms of electromagnetic radiation that cross their event horizons. A black hole in isolation, with no matter falling into it, would be completely dark and silent, detectable only through its gravitational effects on nearby objects or light dot. This silence extends even to the gravitational waves they emit, though these waves can be converted into audible sounds for human appreciation. The chirp of merging black holes, detected by LIGO, is often presented as an rising tone. The waves themselves are not sound. They are oscillations in the fabric of space-time, alternately stretching and compressing distances by tiny amounts as they pass. In the vacuum of space, these oscillations propagate at the speed of light, carrying energy and information about their source across vast cosmic distances. The sensitivity required to detect these waves is almost beyond comprehension. When the first gravitational waves from merging black holes were detected by LIGO in 2015, they changed the length of LIGO's 4-kilometer arms by just 1/10,000th the width of a proton, a distance smaller than the nucleus of an atom. Detecting such minute changes requires extraordinary technological precision, including lasers stabilized to 1 part in a trillion, mirrors polished to atomic smoothness, and sophisticated systems to isolate the detectors from terrestrial vibrations. Yet, despite this silence, black holes can indirectly create some of the most energetic phenomena in the universe. When matter falls into a black hole, it typically forms an accretion disk, a flattened, spiraling structure of superheated plasma. The inner regions of these disks can reach temperatures of millions of degrees, emitting X-rays and other high-energy radiation. In some cases, particularly for supermassive black holes at the centers of galaxies, the energy released by accretion can power jets of particles that extend for thousands or even millions of light years, far larger than the galaxy itself. These jets, though formed near the black hole, are not part of it. They consist of particles, mainly electrons and positrons, sometimes protons, accelerated to nearly the speed of light by complex interactions between the accretion disk, the black hole's rotation, and magnetic fields that thread through the system. The energy for these jets ultimately comes from the gravitational potential energy of the infalling matter, or in some cases, from the rotational energy of the black hole itself, through processes similar to the Penrose process. Let us step back in time once more to consider the quiet life of the stars that formed these black holes. A massive star burns through its nuclear fuel at a prodigious rate, its core a fusion reactor converting lighter elements into heavier ones. Hydrogen fuses into helium, releasing energy that supports the star against collapse. When the hydrogen is depleted, the core contracts and heats until it's hot enough to fuse helium into carbon. This process continues, creating progressively heavier elements: carbon, neon, oxygen, silicon, each stage burning faster than the last. As the star races toward its inevitable end, the life cycle of a massive star is a study in cosmic timescales. A star with 50 times the mass of our Sun might spend only 4 million years fusing hydrogen in its core, compared to the 10 billion years our Sun will spend in this phase. During this main sequence lifetime, the star shines with a brilliant blue-white light, emitting most of its energy in the ultraviolet part of the spectrum. Its surface temperature might reach 40,000 Kelvin or more, compared to the Sun's modest 5,800 Kelvin. Inside such a star, the core temperature reaches 40 million Kelvin or higher, hot enough for hydrogen nuclei to overcome their mutual electrical repulsion and fuse together through quantum tunneling. The primary process is the proton-proton chain, wherefore hydrogen nuclei, protons, combine to form one helium nucleus, releasing energy in the form of gamma rays and neutrinos. This energy, working its way outward through the star's layers, provides the pressure that balances the inward pull of gravity. As hydrogen in the core is converted to helium, the core composition gradually changes. When the hydrogen is nearly exhausted, the core contracts under gravity, heating up in the process. This contraction releases gravitational potential energy, heating the core until it reaches about 100 million Kelvin, hot enough for helium nuclei to fuse into carbon through the triple alpha process. Meanwhile, hydrogen fusion continues in a shell around the core, and the star's outer layers expand dramatically, cooling as they do so. The once blue star becomes a red supergiant, with a surface temperature of perhaps 3,500 Kelvin, but a luminosity hundreds of thousands of times greater than our Sun. The helium burning phase lasts only about 500,000 years. For our massive star, as helium is converted to carbon, the process repeats. The core contracts, heats up, and begins fusing carbon into neon and oxygen at temperatures around 600 million Kelvin. This phase might last only 600 years. Neon burning follows, lasting perhaps a year, then oxygen burning for 6 months, and finally silicon burning, which might continue for just a day. Each of these burning stages proceeds faster than the last because the energy released per fusion reaction decreases as heavier elements are created, while the energy radiated by the star remains roughly constant. The star must burn fuel faster to maintain its energy output. Additionally, at the higher temperatures of advanced burning stages, neutrino production increases dramatically. These ghostly particles carry away energy directly from the core, accelerating its evolution. In the final days of such a star, silicon fuses into iron in the core. This marks the beginning of the end, for iron fusion absorbs energy rather than releasing it. With no outward pressure to counterbalance gravity, the core collapses. The inner layers fall inward at a significant fraction of the speed of light, compressing until they reach nuclear density 4 stars below a certain mass. This collapse is halted by neutron degeneracy pressure, forming a neutron star. But for our more massive stars, even this pressure is insufficient. The collapse continues until a black hole forms a point where matter is compressed beyond our current understanding of physics. The collapse of the core happens with astonishing speed. One moment, the core is a ball of iron and nickel, perhaps the size of Earth, but containing several solar masses of material. The next moment, within milliseconds, electrons are forced into atomic nuclei, combining with protons to form neutrons and releasing neutrinos in a process called electron capture. The core shrinks from thousands of kilometers in diameter to perhaps 30 kilometers, the size of a small city. 4 stars with cores below about 3 solar masses. This collapse is halted by neutron degeneracy pressure, a quantum mechanical effect that prevents neutrons from being packed too closely together. The result is a neutron star, an object so dense that a teaspoonful of its material would weigh billions of tons on Earth. Neutron stars rotate rapidly, sometimes hundreds of times per second, and often have powerful magnetic fields, trillions of times stronger than Earth's. But for stars with more massive cores, even neutron degeneracy pressure is insufficient to halt the collapse. The neutrons themselves are crushed beyond nuclear density, and the collapse continues. According to our current understanding of physics, nothing can stop this collapse once it begins. The core continues to shrink, eventually crossing the threshold, where its escape velocity exceeds the speed of light. At this point, an event horizon forms, and a black hole is born. The outer layers of the star, meanwhile, bounce off the collapsing core and are ejected outward in a supernova explosion. This violent end seeds the surrounding space with heavy elements: carbon, oxygen, silicon, iron, the building blocks of planets, and, eventually, life. In this way, the death of stars enriches the cosmos, providing the raw materials for new generations of stars and planets. The supernova explosion is one of the most energetic events in the universe. For a brief period, perhaps a few weeks, a single exploding star can outshine an entire galaxy of billions of stars. The energy released is staggering, equivalent to the energy our sun will emit over its entire 10 billion year lifetime, concentrated into a few weeks. This energy comes from several sources. The gravitational collapse of the core releases enormous amounts of potential energy, much of which is carried away by neutrinos. These ghostly particles, nearly massless and barely interacting with matter, flow outward from the collapsing core in a burst that carries away about 99% of the supernova's energy. A small fraction of these neutrinos interact with the outer layers of the star, helping to power the explosion. Additional energy comes from nuclear reactions in the shock wave as it propagates through the star's outer layers. The extreme temperatures and pressures in the shock can trigger fusion reactions that create elements heavier than iron, including gold, platinum, and uranium. These processed rapid neutron capture elements can only be formed in the extreme conditions of supernova or neutron star mergers, making them among the rarest elements in the universe. The expanding shell of the supernova, called a supernova remnant, continues to evolve for thousands of years after the initial explosion. As it expands into the surrounding interstellar medium, it sweeps up gas and dust, forming a shock wave that can trigger the formation of new stars. The remnant also enriches the interstellar medium with heavy elements, which will eventually be incorporated into new stars and planets. Some of these elements are essential for life as we know it. Carbon forms the backbone of organic molecules. Oxygen is needed for water and for the energy-releasing reactions in our cells. Phosphorus is a key component of DNA and ATP, the energy currency of life. Iron carries oxygen in our blood. In a very real sense, we are made of stardust. The atoms in our bodies were forged in the hearts of stars and scattered by supernova. Billions of years ago, the connection between black holes and life might seem tenuous. One represents the ultimate end of matter, while the other represents its most complex organization. Yet they are linked through this cosmic cycle of stellar birth, life, and death. The same processes that can lead to black holes also create the elements necessary for life. And the gravitational influence of black holes can trigger the collapse of gas clouds, leading to the formation of new stars and potentially life-bearing planets. As we contemplate these cosmic cycles, the lives and deaths of stars, the formation of black holes, the creation of elements, the emergence of life, we are reminded of our deep connection to the cosmos. Our black holes, born from these stellar deaths, begin their lives in different regions of their host galaxy. They drift through space, their immense gravity occasionally capturing passing stars or gas clouds into orbit. A black hole moving through a dense cloud of interstellar gas might accumulate an accretion disk, a flattened ring of matter spiraling inward. As this matter falls toward the event horizon, it heats up through friction, sometimes reaching temperatures of millions of degrees and emitting X-rays detectable across vast distances. This is how many black holes reveal their presence to astronomers, not through direct observation, but through the light emitted by matter in their gravitational grip. The journey of a solitary black hole through the cosmos is one of profound isolation. Picture such an object, perhaps 15 or 20 times the mass of our Sun, yet compressed into a region smaller than Manhattan Island, moving silently through the vast spaces between stars. Its presence warps the fabric of space-time around it, creating a deep gravitational well that curves the paths of light and matter. Stars that appear close to it in the sky would actually be far behind or in front of it. Their light bent around the black hole's gravity well in a phenomenon called gravitational lensing. If we could somehow observe this effect, we might see multiple images of the same star, or stars appearing to move in strange, non-Newtonian ways as the black hole passes in front of them. The black hole itself remains invisible, a perfect absence against the backdrop of stars. But as it moves through regions of interstellar gas and dust, its gravity begins to draw this material inward. At first, the process is gentle. Individual atoms and dust grains, perhaps light years away, feel a subtle tug toward the black hole. Their paths, which might otherwise have taken them in straight lines through space, begin to curve. Over decades or centuries, these particles spiral inward, gradually approaching the invisible gravitational center. As more material gathers around the black hole, the particles begin to interact with each other. Collisions between atoms and dust grains convert some of their gravitational potential energy into heat. The material flattens into a disk, not because the black hole's gravity is stronger at its equator than at its poles, it isn't, but because the random motions of the infalling matter average out over time. and collisions between particles moving in different directions cause them to settle into the lowest energy configuration, a thin, rotating disk. This accretion disk grows over time, fed by the constant infall of new material. Near the outer edges of the disk, the matter might be cool enough to exist as dust or even molecular gas, but as it spirals inward, it heats up dramatically. The inner regions of the disk can reach temperatures of millions of degrees, hot enough to emit X-rays and gamma rays. The disk glows with a fierce light, a beacon in the darkness that signals the presence of the invisible black hole at its center. The physics of accretion disks is complex and beautiful. The material doesn't simply fall straight into the black hole. It orbits, much like planets orbit the sun. But unlike our solar system, where the planets' orbits are stable over billions of years, the matter in an accretion disk gradually loses energy and angular momentum through viscous interactions. This causes it to spiral inward, eventually crossing the event horizon and adding to the black hole's mass. The innermost regions of the accretion disk experience extreme conditions. Here, the material orbits at a significant fraction of the speed of light. Relativistic effects become important. Time dilation stretches seconds into hours from an outside observer's perspective, and the Doppler effect causes the light from the approaching side of the disk to appear blue-shifted, while light from the receding side appears red-shifted. If the black hole is rotating, it drags the surrounding spacetime with it, causing the inner edge of the accretion disk to precesses like a wobbling top. Some of the energy released by the infalling matter doesn't go into heat and radiation, but instead powers jets of particles that shoot outward from the black hole's poles at nearly the speed of light. These jets can extend for thousands or even millions of light years, far larger than the galaxy that hosts the black hole. They're thought to form through complex interactions between the accretion disk, the black hole's rotation, and magnetic fields that thread through the system. The jets carry away energy and angular momentum, allowing more matter to fall into the black hole as our solitary black hole continues its journey through the galaxy. It might eventually encounter regions where stars are more densely packed, perhaps the galactic core or a globular cluster orbiting in the galactic halo. Here, the average distance between stars might be measured in light-weeks rather than light-weeks rather than light-years. In such environments, the probability of a close encounter with another star or another black hole increases dramatically. The black hole's gravity might capture a passing star into orbit, creating a binary system where a visible star orbits an invisible companion. Such systems, called X-ray binaries, when the black hole is actively accreting matter from its stellar partner, have been observed throughout our galaxy. By studying the orbit of the visible star, astronomers can infer the mass of its unseen companion. If this mass exceeds about 3 solar masses, the theoretical maximum for a neutron star, the companion is likely a black hole in some cases. A black hole might pass close enough to a star to disrupt it without capturing it. The star would be stretched and distorted by tidal forces, the difference in gravitational pull between the near and far sides of the star. If the encounter is close enough, the star might be completely torn apart in what astronomers call a tidal disruption event. About half the stellar material would be flung away into space, while the other half would fall toward the black hole. creating a temporary accretion disk and a bright flare of radiation that might last for months or years before fading, over millions or billions of years. The random movements of stars and black holes occasionally bring to black holes close enough for their gravitational fields to capture each other. When this happens, they begin orbiting a common center of mass, forming a binary black hole system. Such a pairing might occur in several ways. Perhaps the black holes formed from a binary star system, as in our story, or perhaps they encountered each other by chance in the dense core of a galaxy or star cluster. The formation of a binary black hole through random encounter is a delicate dance of gravity. Two black holes, each moving along its own path through a star cluster, might pass close enough to influence each other gravitationally. But a simple close passage isn't enough to form a bound system. One or both black holes must lose energy during the encounter. This might happen if a third star or black hole is nearby and interacts with the pair, carrying away some of their kinetic energy. Or it might occur through gravitational radiation, even during their first close passage. The black holes emit gravitational waves that carry away a tiny fraction of their energy. If enough energy is lost, the black holes can't escape each other's gravitational pull. They begin orbiting their common center of mass, forming a binary system. At first, this orbit might be highly elliptical, with the black holes swinging far apart at a postron, the farthest point in their orbit, and coming relatively close at periastron, the nearest point. Over time, gravitational radiation will cause the orbit to decay and become more circular, but this process might take billions of years if the black holes are initially widely separated. Binary black holes can also form from binary star systems. If two massive stars are born as a binary pair, they might remain together throughout their lives, eventually dying and forming two black holes that continue to orbit each other. This pathway is thought to be common, as many massive stars form in binary or multiple systems. The evolution of such a system is complex, with the stars potentially exchanging mass during their lifetimes, and their supernova potentially disrupting the binary if the explosions are asymmetric. But if the system survives these challenges, it can produce a binary black hole directly, without needing a chance encounter in a dense stellar environment. A third formation pathway involves dense stellar environments, like globular clusters or the cores of galaxies. In these regions, black holes tend to sink toward the center due to a process called dynamical friction as they move through the cluster. Gravitational interactions with lighter stars cause the black holes to lose energy and spiral inward. This concentrates black holes in the cluster core, increasing the probability of binary formation. Once formed, these binaries can interact with other stars or black holes, potentially exchanging partners in complex three-body interactions that can lead to tighter binaries with more equal masses. Once bound together by gravity, the black holes become invisible companions, their presence detectable only through their effects on nearby matter or through the gravitational waves they emit. If one or both black holes have an accretion disk, the complex gravitational interactions might create periodic flares or variations in brightness that hint at the binary nature of the system. But in many cases, binary black holes orbit in darkness. their dance unseen by any observer. The gravitational bond between them is like an invisible thread connecting them across the void. This bond gradually tightens as the system loses energy through gravitational radiation. The black holes spiral inward, their orbits becoming smaller and more circular over time. This inspiral phase might last for billions of years, a patient approach governed by the inexorable mathematics of general relativity. The rate at which the orbit decays depends strongly on the separation between the black holes. When they're far apart, the gravitational waves they emit are weak, and the orbit changes very slowly. A binary with black holes separated by, say, 1 astronomical unit, the distance from Earth to the Sun might take longer than the current age of the universe to merge. But as the black holes get closer, the process accelerates. The gravitational waves become stronger, carrying away more energy, causing the black holes to spiral inward more rapidly. This creates a characteristic pattern in the gravitational wave signal, a chirp that increases in both frequency and amplitude as the black holes approach merger. The mathematics describing this pattern was worked out decades before gravitational waves were directly detected, allowing scientists to create templates that could be matched against detector data to identify genuine signals from binary black hole mergers. The orbital evolution of a binary black hole system is described by a set of equations derived from Einstein's theory of general relativity. For most of the inspiral phase, when the black holes are still relatively far apart, these equations can be approximated using a technique called the post-Newtonian expansion, essentially a series of corrections to Newtonian gravity that account for relativistic effects. As the black holes get closer, more terms in this expansion become important, and the dynamics become increasingly complex. In the final stages of the inspiral, when the black holes are very close, the post-Newtonian approximation breaks down, and full numerical relativity simulations are needed. These simulations solve Einstein's field equations directly, tracking the evolution of spacetime itself as the black holes orbit and eventually merge. Such simulations require supercomputers and sophisticated numerical techniques, as they must handle the extreme curvature of spacetime near the black holes and the complex interactions between them. Imagine these two massive objects, each perhaps 20 or 30 times the mass of our Sun, yet compressed into regions smaller than a city, orbiting each other in the darkness of space. Their event horizons are separate bubbles in spacetime, each marking a boundary beyond which nothing can escape. As they orbit, they create ripples in the fabric of spacetime gravitational waves that propagate outward at the speed of light, carrying energy away from the system. If we could somehow observe this binary system up close, though still at a safe distance, what would we see? With our eyes alone, we would see nothing, for black holes emit no light. But if the black holes have accretion disks, we might observe two glowing rings of superheated gas, distorted by their rapid orbital motion and the extreme curvature of spacetime near the event horizons. As the black holes orbit, these rings would appear to dance around each other, their light brightening and dimming as the Doppler effect alternately blue shifts and red shifts the radiation. The orbital motion itself would be too slow to perceive directly if the black holes are widely separated. A binary with black holes orbiting at, say, 1/10 of a light year apart might have an orbital period of decades or centuries. But as the black holes spiral closer together, their orbital period decreases. When they're separated by just a few hundred kilometers, they might orbit each other several times per second, creating gravitational waves with frequencies in the audible range, though still far too subtle to detect without specialized instruments. For most of their binary life, these gravitational waves are extremely weak, causing space-time to stretch and compress by infinitesimal amounts. The frequency of these waves matches the orbital frequency of the black holes, perhaps one cycle every few hours or days, depending on their separation. As the black holes spiral closer together, both the amplitude and frequency of the gravitational waves increase, though they remain far too subtle to detect without extremely sensitive instruments. The nature of these gravitational waves is worth contemplating. Unlike electromagnetic waves, which propagate through spacetime, gravitational waves are oscillations of spacetime itself. They alternately stretch and compress space in directions perpendicular to their direction of travel. If a gravitational wave traveling along the z-axis passes through a ring of particles arranged in a circle in the xy plane, the ring would be stretched into an ellipse along the x-axis while being compressed along the y-axis, then stretched along the y-axis while being compressed along the x-axis, and so on as the wave passes. This stretching and compressing is incredibly subtle, even for the strongest gravitational waves detected so far. The change in distance is on the order of 10 to 18 meters, about 1,000th the width of a proton. Detecting such minute changes requires instruments of extraordinary precision, which we'll explore later when we discuss LIGO and other gravitational wave observatories. As the black holes continue their spiral inward, the physics becomes increasingly complex. When they're very close, within about 10 times the sum of their Schwarzschild radii, the radius of a non-rotating black hole's event horizon, their event horizons begin to distort each other through tidal forces. The spacetime between them becomes highly curved, and the orbital dynamics can no longer be accurately described by simple Keplerian motion. Numerical relativists use supercomputers to solve Einstein's field equations and simulate these final orbits, a computational challenge that requires tracking the evolution of spacetime itself in 3 dimensions over time. After thousands, perhaps millions of orbits, the black holes enter the final phase of their cosmic dance. Now, separated by perhaps just a few hundred kilometers, they orbit each other at a significant fraction of the speed of light. The gravitational waves they emit become stronger and higher in frequency, carrying away energy at an accelerating rate. This causes the orbit to decay more rapidly, creating a feedback loop. Closer orbits produce stronger waves, which cause faster decay, bringing the black holes ever closer together. In the last few moments before merger, the black holes complete their final orbits in a fraction of a second. The gravitational waves reach their peak strength, briefly carrying away energy at a rate exceeding the combined light output of all the stars in the observable universe. Yet, this tremendous release of energy happens in perfect silence, detectable only as a subtle stretching and compressing of spacetime itself. The final moments before merger are a blur of extreme physics. The black holes orbit each other hundreds of times per second. their event horizons distorted by each other's gravity into teardrop shapes pointing toward their companion. The space between them churns like water in a whirlpool, dragged around by the rapid orbital motion. Gravitational waves pour outward in all directions, carrying away energy and angular momentum, causing the orbit to decay ever more rapidly, and then, in a final plunge, the event horizons merge. This is not a physical collision in the conventional sense. There are no surfaces to impact, no sound of collision, no flash of light. Instead, it is a merger of space-time geometries, as two separate regions of extreme curvature combine into one. The mathematics describing this merger are among the most complex in physics, requiring supercomputers to solve the equations of general relativity in their full, non-linear glory. For a brief moment during the merger, the combined system is asymmetrical, with gravitational waves being emitted more strongly in some directions than others. This creates a recoil effect, potentially kicking the newly formed black hole in a particular direction at hundreds or even thousands of kilometers per second. Such a kick might eject the black hole from its host star cluster, or, in extreme cases, from its galaxy entirely, sending it on a lonely journey through intergalactic space. After the merger, the system quickly settles down. The newly formed black hole, now, with a mass equal to the sum of its progenitors, minus the energy radiated away as gravitational waves, typically a few percent of the total mass, enters a brief ring-down phase. Like a struck bell, the distorted event horizon oscillates, emitting gravitational waves at characteristic frequencies that depend on the black hole's mass and spin. These oscillations dampen quickly, and within a fraction of a second, the black hole reaches its final, stable state, a perfect geometric object described by just three parameters: mass, electric charge, and angular momentum. This simplicity is profound. No matter how complex the objects that formed the black hole, no matter their composition or structure, the final black hole remembers only these three properties. All other information about the progenitor objects is, in some sense, lost, or perhaps encoded in ways we don't yet understand, leading to the famous black hole information paradox that continues to challenge theoretical physicists. The gravitational waves from the merger, meanwhile, continue their journey outward through space at the speed of light. After traveling for perhaps billions of years, growing ever fainter with distance, these ripples might pass through our solar system, stretching and compressing space itself by a tiny fraction of the width of an atom. This subtle distortion is what our gravitational wave detectors are designed to measure. I understand you're looking for a very substantial expansion of the text in a single response. While I'll do my best to provide a thorough expansion, please be aware that there are limitations to how much content I can deliver in one response. Let me create an expanded version of your script about black hole mergers that maintains the meditative, sleep-friendly tone while adding scientific depth in the last few moments before merger. The black holes complete their final orbits in a fraction of a second. The gravitational waves reach their peak strength, briefly carrying away energy at a rate exceeding the combined light output of all the stars in the observable universe. Yet this tremendous release of energy happens in perfect silence, detectable only as a subtle stretching and compressing of space-time itself. This final dance of the black holes represents one of the most extreme events in our universe. As they approach their ultimate union, the black holes orbit each other with increasing speed, completing their final circuits in mere milliseconds. Their velocities approach a significant fraction of the speed of light, perhaps 30% or more, creating profound distortions in the surrounding space-time. The gravitational waves they emit now carry away energy at a staggering rate, briefly exceeding watts, more power than all the stars in the observable universe combined. To put this in perspective, our Sun emits about 3.8 times watts of electromagnetic radiation. The entire Milky Way galaxy, with its hundreds of billions of stars, produces perhaps 1037 watts. Yet in the final moments of a binary black hole merger, gravitational wave emission can briefly exceed watts, 13 orders of magnitude, more powerful than our galaxy. This makes the merger, for that brief instant, the most energetic single event in the universe since the Big Bang itself. Yet, despite this enormous energy release, the merger happens in complete silence. Unlike electromagnetic waves, which can be absorbed and re-emitted by matter, gravitational waves pass through almost everything with minimal interaction. They carry away energy and angular momentum from the binary system, but they do so without sound, without light, without any form of radiation that our unaided senses could detect. Only the most sensitive instruments ever built by humans can register their passing. The frequency of these gravitational waves increases dramatically during the final approach, when the black holes are still relatively far apart, say, orbiting each other once every few hours. The gravitational waves they emit have frequencies measured in microhertz, far too low for current detectors to measure. But as the orbit shrinks and accelerates, the frequency rises. In the final seconds before merger, the frequency sweeps upward through the audio range from tens of hertz to several hundred hertz, creating what scientists call a chirp signal. If converted to sound waves, this signal would resemble a rising whistle, increasing in both pitch and volume before suddenly cutting off at the moment of merger. The shape of this chirp carries detailed information about the merging black holes, their masses, their spins, their orbital eccentricity, and their distance from Earth. By carefully analyzing the waveform, scientists can reconstruct many properties of the source, even though the black holes themselves emit no light. This is the power of gravitational wave astronomy. It allows us to hear events that we cannot see, providing a completely new way to study the universe. The final orbits of the black holes follow paths that no longer resemble the ellipses of Keplerian motion. At these extreme velocities and close separations, the full nonlinear nature of Einstein's field equations becomes apparent. The black holes no longer simply orbit each other, they orbit in space-time that is itself being dragged around by their motion, creating a complex dance that can only be modeled using sophisticated numerical simulations. As they spiral ever closer, the event horizons of the black holes begin to distort. No longer perfect spheres for non-rotating black holes, or oblate spheroids for rotating ones. They stretch toward each other like cosmic teardrops, responding to the tidal forces of their companion's gravitational field. The space between them churns like water in a whirlpool, dragged around by their rapid orbital motion. In the final moments, when the black holes are separated by just a few times the sum of their Schwarzschild radii, they complete several orbits per second, their horizons almost touching as they whirl around their common center of mass. The gravitational waves emitted during these final orbits carry away not just energy, but also angular momentum. This loss causes the orbit to decay even more rapidly, creating a feedback loop that accelerates the merger. The black holes spiral inward faster and faster, their orbital frequency increasing exponentially as they approach the final plunge. This creates the characteristic chirp pattern in the gravitational wave signal, a rapid increase in both frequency and amplitude that serves as a distinctive signature of binary black hole mergers. And then, in a final plunge, the event horizons merge. This is not a physical collision in the conventional sense. There are no surfaces to impact, no sound of collision, no flash of light. Instead, it is a merger of space-time geometries as two separate regions of extreme curvature combine into one. The mathematics describing this merger are among the most complex in physics, requiring supercomputers to solve the equations of general relativity in their full, nonlinear glory. The merger itself happens remarkably quickly. From the moment the event horizons first touch to the formation of a single, unified horizon takes perhaps a millisecond or less. During this brief interval, space-time undergoes a topological transformation as two separate closed surfaces combine into one. This process, called a pair of pants transition by relativists, because the space-time diagram resembles a pair of pant legs joining at the crotch, represents a fundamental change in the causal structure of space-time. Before the merger, each black hole has its own event horizon, a boundary in space-time beyond which nothing can escape. These horizons are separate, allowing light and matter to pass between them, though the intense gravity would make such passage difficult. After the merger, a single event horizon forms, enclosing both former black holes in a common region of no return. The transition between these states involves complex nonlinear dynamics that push Einstein's equations to their limits. The mathematics describing this process is so complex that for decades, scientists could only approximate it. Early attempts used perturbation theory or other simplifications, but these broke down as the black holes approached merger. It wasn't until the early 2000s, with the development of advanced numerical techniques and powerful supercomputers, that physicists could directly simulate the merger process by solving Einstein's field equations in their full, nonlinear form. These numerical relativity simulations divide spacetime into a grid of points, tracking how the geometry evolves at each point as the black holes orbit and merge. The calculations are enormously demanding, requiring thousands of processors even on supercomputers. The first successful simulation of a black hole merger, achieved in 2005 by Franz Pretorius, was a landmark in theoretical physics, opening the door to detailed studies of these extreme events. The challenge of simulating black hole mergers lies in the nature of Einstein's field equations themselves. These equations, which describe how matter and energy curve spacetime, are a set of 10 coupled, nonlinear partial differential equations. Their nonlinearity means that the curvature caused by two black holes is not simply the sum of the curvatures that each would produce individually. Instead, the curvatures interact in complex ways, requiring sophisticated mathematical techniques to model accurately. Moreover, the simulations must handle the extreme curvature near the black hole's event horizons without developing singularities that would crash the computation. Various techniques have been developed to address this challenge, including excision, removing the region inside the event horizon from the computational domain, moving punctures representing the black holes as punctures in the computational grid that move through it, and characteristic evolution using coordinates adapted to the propagation of light. Modern simulations can now track the entire merger process with high precision, from the late-in spiral through the merger itself and into the subsequent ringdown phase. They reveal the complex dynamics of spacetime as the black holes combine, how the event horizons distort and merge, how gravitational waves are generated and propagate, and how the final black hole forms and settles down. These simulations were crucial for interpreting the first gravitational wave detections, providing templates that could be matched against the observed signals. The merger process itself, though brief, involves several distinct phases. First, the event horizons touch, forming a bridge between the two black holes. This bridge rapidly expands as the horizons merge, creating a single, highly distorted event horizon that encompasses both former black holes. The shape of this merged horizon evolves quickly, oscillating as it settles toward its final equilibrium state. During this process, the topology of the event horizon changes. Before the merger, we have two separate spherical, or nearly spherical, horizons. After the merger, we have a single connected horizon. This topological change is a key feature of the merger process, representing the unification of two separate causal structures into one, the interior of the newly formed black hole. Beyond the event horizon remains hidden from external observers. According to classical general relativity, the singularities from the original black holes merge to form a single central singularity. However, many physicists believe that quantum effects would prevent the formation of a true singularity, perhaps replacing it with an extremely dense but finite quantum state. The nature of this interior region remains one of the great unsolved problems in theoretical physics, lying at the intersection of general relativity and quantum mechanics. For a brief moment during the merger, the combined system is asymmetrical, with gravitational waves being emitted more strongly in some directions than others. This creates a recoil effect, potentially kicking the newly formed black hole in a particular direction at hundreds or even thousands of kilometers per second. Such a kick might eject the black hole from its host star cluster, or, in extreme cases, from its galaxy entirely, sending it on a lonely journey through intergalactic space. This recoil phenomenon, sometimes called a gravitational rocket, is a direct consequence of momentum conservation. When gravitational waves carry away momentum preferentially in one direction, the black hole must recoil in the opposite direction to conserve the total momentum of the system. The strength of this recoil depends on the mass ratio of the merging black holes and their spin orientations. For black holes of equal mass with no spin, the recoil velocity might be around 170 kilometers per second, fast enough to escape from a globular cluster, but not from a galaxy. But if the black holes have significant spins that are misaligned with each other, or with the orbital angular momentum, the recoil can be much stronger. Numerical simulations have found cases where the merged black hole could be kicked at velocities exceeding 4,000 kilometers per second, fast enough to escape from even the most massive galaxies. The mechanism behind these extreme recoils involves a complex interplay between the black hole's spins and their orbital motion. When the spins are aligned with each other and with the orbital angular momentum, the gravitational wave emission is relatively symmetrical, resulting in minimal recoil. But when the spins are misaligned, they can create asymmetries in the emission pattern that lead to significant net momentum being carried away in a particular direction. The strongest recoils occur for black holes of nearly equal mass, with large, anti-aligned spins lying in the orbital plane. In such configurations, the spins create a bobbing motion as the black holes orbit, causing them to move alternately toward and away from each other in addition to their orbital motion. This bobbing motion leads to asymmetric gravitational wave emission that can result in extreme recoils. Such high-velocity black holes, ejected from their host galaxies, would become truly intergalactic wanderers, moving through the near-perfect vacuum between galaxies. They would have little opportunity to accrete matter or interact with other objects. They would be nearly impossible to detect directly, though their departure might leave subtle signatures in their former host galaxies, perhaps a disturbed region where stars were scattered by the black hole's passage, or an off-center supermassive black hole in a galaxy that experienced a merger with a recoiling black hole's former host. The possibility of black hole ejection has important implications for the growth of supermassive black holes in galaxy centers. If mergers frequently result in high-velocity recoils, this could limit the ability of black holes to grow through successive mergers, as many would be ejected before they could participate in additional mergers. This might help explain why we don't observe black holes with masses much above 1010 solar masses, despite theoretical models suggesting they could grow larger. Astronomers have searched for evidence of recoiling supermassive black holes, looking for quasars, active galactic nuclei powered by black holes that are offset from the centers of their host galaxies, or that show velocity shifts in their emission lines relative to their host galaxies. Several candidates have been identified, though confirming their nature remains challenging. If verified, these objects would provide important constraints on the frequency and magnitude of recoils in black hole mergers. After the merger, the system quickly settles down. The newly formed black hole, now with a mass equal to the sum of its progenitors, minus the energy radiated away as gravitational waves, typically a few % of the total mass, enters a brief ring-down phase. Like a struck bell, the distorted event horizon oscillates, emitting gravitational waves at characteristic frequencies that depend on the black hole's mass and spin. These oscillations dampen quickly, and within a fraction of a second, the black hole reaches its final stable state, a perfect geometric object described by just 3 parameters: mass, electric charge, and angular momentum. The ring-down phase represents the final stage of the merger process as the newly formed black hole settles into its stable configuration, the distorted event horizon. Initially far from the perfect geometric shape of an isolated black hole, oscillates with characteristic patterns called quasi-normal modes. These oscillations are damped. They decay exponentially with time, As the black hole radiates away, the distortions through gravitational waves, the frequencies and damping times of these quasi-normal modes depend only on the black hole's mass, spin, and charge. For a Schwarzschild, non-rotating, uncharged black hole, the dominant oscillation has a frequency of approximately Ca 10 gm, where c is the speed of light, g is the gravitational constant, and m is the black hole's mass. For a stellar mass black hole of 30 solar masses, this corresponds to a frequency of about 120 Hz within the audio range, though the oscillations typically last only a few milliseconds. For a rotating black hole, the quasi-normal modes are more complex, with frequencies that depend on both the mass and the spin. Higher spin rates generally lead to higher frequencies and longer damping times. By measuring these frequencies in the gravitational wave signal, scientists can determine the properties of the final black hole, providing a consistency check on the parameters inferred from the inspiral and merger phases. The ring-down phase is particularly interesting to theoretical physicists because it provides a direct test of the no-hair theorem, the prediction from general relativity that black holes are completely characterized by just three parameters: mass, charge, and spin. If this theorem is correct, the frequencies and damping times of the quasi-normal modes should follow specific relationships. Any deviation from these relationships would suggest that black holes have additional properties beyond the standard three, potentially pointing to new physics beyond general relativity. The quasi-normal modes themselves can be understood as perturbations of the black hole's gravitational field that propagate and decay with time. They are called quasi-normal because, unlike the normal modes of a vibrating string or drum, they decay with time due to the emission of gravitational radiation. Each mode is characterized by three integers: a harmonic index L, an azimuthal index M, and an overtone index N. The dominant mode, which carries most of the energy and is most easily detected, is the L equals 2, M equals 2, N equals 0 mode, often called the quadrupole mode. Within a fraction of a second, these oscillations die away and the black hole settles into its final, stable state. The event horizon now has the perfect geometry predicted by the Kerr metric for a rotating black hole, or the Schwarzschild metric for a non-rotating one. All traces of the violent merger that formed it have vanished, except for the black hole's mass, spin, and any electric charge it might possess. This simplicity is profound. No matter how complex the objects that formed the black hole, no matter their composition or structure, the final black hole remembers only these three properties. All other information about the progenitor objects is, in some sense, lost, or perhaps encoded in ways we don't yet understand, leading to the famous black hole information paradox that continues to challenge theoretical physicists. The no theorem, the term hair, referring metaphorically to distinguishing features, is one of the most remarkable predictions of general relativity. It states that once a black hole forms and settles down, it is completely characterized by just three parameters: mass, electric charge, and angular momentum spin. All other information about the matter that formed the black hole, its composition, structure, distribution, quantum states, appears to be lost when the matter crosses the event horizon. This loss of information creates a profound puzzle when combined with quantum mechanics. which holds that information cannot be destroyed. According to quantum theory, if you know the exact state of a system at one time, and you know the laws governing its evolution, you should, in principle, be able to determine its state at any other time, both in the future and in the past. The evolution should be reversible. But black holes seem to violate this principle, as they appear to destroy information about the matter that forms them. This conflict between general relativity and quantum mechanics has led to decades of theoretical debate and speculation. Stephen Hawking brought the issue to prominence in the 1970s when he discovered that black holes should emit radiation, now called Hawking radiation, due to quantum effects near the event horizon. This radiation appears to be purely thermal, characterized only by the black hole's temperature, which depends on its mass and contains no information about the matter that formed the black hole. Asterisk.